Yeah, hope everybody,
Am I taking over?
yeah, hope everybody's safe and healthy. I will share my All right, so let me know if you can't see the screen. Otherwise, we will continue. So hopefully you've taken a look at this problem, but if not, let me briefly go over it. So a very simple problem in terms of the scope. It's given a binary tree, return all the root to leaf paths. So this is a binary tree. The root is node with value 1, and it has two baby children nodes, and each have values 2 and 3. And then node 2 has another child node, which has a value of 5. So we can see that all the root to leaf paths, and a leaf is defined as a node with no children, is 5 and 3. Remember, 2 is not a leaf because it does have one child. So all the root to leaf paths, all the legal paths are 1 to 5 and 1 to 3. So how do we do this programmatically in terms of finding all the possible binary tree paths that go from roots all the way to a leaf? And there's two classic ways of doing this, and it's breadth first search and depth first search. Now, you've seen my problems from the past few weeks. I've done a lot of depth first search solutions because a lot of problems lend themselves to this algorithmic traversal of a tree. And it also, of course, lends itself to a graph because a tree itself is just a subset of a graph. You can see that you can call this a graph if you want, but you can see that this tree is just a very simple form of a graph. So let's get started. So I'm going to do both of the solutions, but this will actually take a lot quicker than you might imagine because a breadth first search and a depth first search are very similar to each other. They're both traversing the entire tree, but they only differ in terms of the container they use in terms of traversing. So breadth first search does it in terms of exactly as it says. It does it by looking at breadth. So in terms of traversing this tree, it's going to start with the root, node 1, then it's going to go to 2 and 3, and then it's going to go to 5. In terms of a depth first search, it's going to go deep in terms of one path before it explores other paths. So depth first search is going to go through 1, 2, 5, and then go to 1, 3. So the way this is accomplished programmatically is that a breadth first search uses what is known as a queue data structure. So let's write it out. So I'm going to write out a function. We're just going to pass out roots. And the reason why I want to write out a function instead of just doing breadth first search is because we're going to write out a function for depth first search as well. So we're going to write out breadth first search, and then it's going to have a roots. And now here comes the fun part. This is, of course, we have to have all the paths. Let's just call this. So LeetCode expects the outputs to be a list of strings. So we're going to initialize that initial output in terms of this variable paths of being a list, and then we're going to push in the possible paths as strings into this list, and we're going to return paths as our answer. And now we have all this white space to actually write the algorithm. So a queue is uses first in, first out in terms of ordering. The classic way it's done in Python is use the queue structure, but I can actually for the sake of simplicity, I'll just make this a list, and it's going to be a list of roots and a possible path. In which case, we're just going to start with an empty string. So we can actually mimic a queue data structure by just using a list or an array. But we have to remember we can't, in terms of pulling stuff out of this queue, we can't pull it from the end of the list. We have to pull it at the beginning of the list. Or if you decide to do that, you have to make sure that whenever you're pulling stuff from this list, that you're appending it in the opposite direction, at the other end of the queue. Otherwise, it wouldn't be a queue; it would be a stack. Because if you're appending and pulling stuff from, or popping stuff from this queue at the same time and there's the same end, let's say like you're doing it at the very last element, then that would be a stack, and it would not be, even though it's using the same list data structure, it would not be considered a queue first in, first out movement. So now, while this queue exists, so what we've done now is I've initialized the first node in the queue, which is just our roots, and our root is going to be, this test case is going to be a list of 1, 2, 3, null, 5, and this is just representation of this binary tree into list form. So you can see that 1 is our first root, there shouldn't be any controversy over that, and then you can see 2 and 3 are both children of this initial node. So it's a little bit confusing in the sense that 2 and 3 are in this order, but this is how we represent trees into a list. And you can see a null and a 5. This null and 5 are actually children of not the prior index node, but the one before that. So you can see that 2 and 3 are both children of the first. And you can see that null and 5 are children of 2. And if we had additional nodes in this tree, the 2 additional nodes would be children of 3, and so on and so forth. And the 2 additional nodes after that would be children of this node at position 0, 1, 2, and position 3. So that's how we represent a tree in list form. So we're initializing our queue with the first node, which is the root, and a possible path, which is currently empty right now. So now let's implement a breadth-first search. So we have to, this queue is meaningless by itself. What's really important is that we actually pull stuff out of this queue. So we're going to do queue.pop. I'm just going to pop the first element because I'm going to append elements to the very end. So it's going to follow that first in, first out movement. And if this node, which is currently our root node, does not have a left node and it does not have a right node, it means that we have a solution. So we're going to append to our output list of paths a solution of, I'm going to use the F statement way of formatting a path, and we want the node value, and that would be the end of it in terms of this possible solution. However, if we haven't hit the end, we have to keep traversing, and we check to see if the current node that we're on, right now we're just in the root phase. Let's see if this node has a right, and if it does have a right, we need to append additional things to this queue. So we're going to append another tuple with node.left, and here comes the fun part. We're increasing the length of our list. Well, not the length of the list, but we're adding a path to our string path, and this string path will represent a total legal path in its own right. So, for example, we're going to be adding a 1, 2, 5 path, and then this path will be slowly increased in terms of its length, but it is a string. So let me write this out, and LeetCode expects us to have this little arrow sign in terms of what the string is, so we're going to write that. And now we made this tuple. So let's copy this. Right, so let's copy that, and then by symmetry, let's explore the left node. It's more intuitive. We can move this left node to the. We can first explore. We can check the left node, and then because we read from left to right, probably a little bit more intuitive. We first check the left node, and then. Right, and then yeah, by symmetry, we're going to check the left node, and we're going to append this node. If there is a node that exists, and we can see that we start the root node, and we're going to, we see that it does not have no children. So repeat again, it has children, so we're going to skip over this initial if statement. We see that it has a left child, so we're going to append that left child node into the queue, and then we're going to increase our path from 1 to 2. So, and we're going to keep doing this until we've also done 1 to 3. And we can see that 3 that has no children, so that will be a legal path, 1 to 3, and then in the node remaining in the queue will be 2 to 5, and we can see that 2 to 5 is valid, and it's going to finish that path of 1 to 5. So the easiest way to visualize this is, let me print out the queue, and let me print out path. Here. All right, so let's check out the outputs. Return self. Oh, sorry. Yeah, this is just BFS. And you can see in a depth first search, I just want to make sure we really get the breadth first search, because depth first search is literally just substituting this queue, and all this code is going to be almost exactly the same as a breadth first search. So in this BFS, you can see that we start with a queue of 1, 2, 5, and you can see the root node. It's kind of not very intuitive if you get used to it in terms of, but this is actually just the root node, and you can see its pointers to its references to its children nodes, and you can see the references that its children nodes has to its own children, and you can see that is our queue initially just has the root node, and with all its references, of course, to its children, so that's why we're able to traverse it by doing if node.left and if node.right. And you can see that we first append the 1 to 3 node path, and then we append the 1 to 5 path. And this should make sense because remember, in the breadth first search, we're first doing 1, 2, 3, then 5. So of course, the 3 terminates earlier than us going to the next level of the tree and then finding the 1, 2, 5 path. So that's what breadth first search is, and you can see just in the manner of like the order in which the paths are appended, that's the case. And you can step through this in terms of exactly how it works, but that's in essence how it works. First, we start with the root node, we pop it out, so the queue now has no elements. We find out there's a left node, so we push it back in the queue. So now the queue has node 2 with its reference to its child node of 5, but you can see the path beginning to take form because now we have the 1 to arrow here. And then the queue, because we also did if node.right, also has the node 3 here, and also the beginnings of the path here, 1 path here. And then you can see, of course, we pop out the first element, the first node, and now our queue just has the remaining node of 3 from initially the 4 here. And we did the if node.left on the pop out node, which was the node of 2, and you can see that it does have indeed a node.right. So we push that, we append that at the end of the queue of the node 5. And you can see that when we pop out this queue of node 3, we see that it has no children, so it's going to append to our output paths answer, and that will be the initial path of 1 to 3. And then you can see that our remaining node in the queue is node 5, and you can see that it's, as expected, the path begins 1 to 2. And then once we pop it out of the queue has no more elements. The path is 1 to 2. We can see that the node that we're currently doing, the last node is node 5. Node 5 has no children, so we append it and complete the path of 1 to 2, and we complete the 5 here. So that's breadth first search. In terms of depth first search, which is my favorite, I'm going to do it iteratively. You've seen me done it recursively like a million times at this point. And I always like a recursive solution, but the recursive solution is just like a little bit, it's almost exactly the same as iterative, but there's like a mental leap that you have to make. Whereas if you do it iteratively here, it's it's just, you can see the classic symmetry it has with breadth-first search. So it's actually, we're just going to call it a stack. But remember, it's still using a list data structure in Python, so we don't have to change that. And then we just have to rename all this fun stuff. Let's print out the stack, and instead of popping it at the initial element, this is literally the only change I'm making besides renaming here. I'm just going to pop it at the very last, because the stack is last in, first out, and I'm going to still append it to the very end. I'm just renaming Q here, and you can see, and then of course, let's, instead of doing breadth-first search, let's do the depth-first search function we defined here. And if all goes according to plan, some indentation. All right, let's see if this works. All right, yep, still goes according to plan. You can see in terms of the stack, the depth-first search does nearly the same as the breadth-first search. And in terms of walking through it, you can see that initially, so let me print out this. Oh, so you can see that right now it's still a list, but I'm now, instead of calling it a queue, I'm going to refer to it as a stack, because now we're popping and pinning it to the very end instead of popping it at the beginning and pinning at the end. So it's the last in, first out right now. And you can see we start with the root node in the stack. It's the node of 1 and all its references to all its babies. And then we pop it out of the stack, and now we have node 2 with its reference to node 5 and node 3 with no children. You can see initial path being built here. And then we pop it out node 2, and we can see that node 2 has no left child, but it has a right child of node 5. And you can see the initial build here of 1. And then we pop it out in terms of, oh wait, sorry. So we're popping out at the very end. So you can see that our node 2 to 5 is still in the stack, because now we're popping out node 3. And you can see that node 3 is gone, and it will build out the initial path of 1 to 3, because we've already taken care of node 3. And then you can see, then we return back to node 2 and 5, which has been patiently waiting in the stack, and now we are able to pop out node 2, and then node 2 has the right reference to node 5, and then we pop out node 5, and then we complete the path from 1 to 5. And let's submit the depth-first search. None-type object has no attribute left. Not node left and not node right. I think what we should do is check to make sure that we actually have a root. It's not node left. So let's do it here. If not, yep, and that's the solution.
Very good.
That's just a guard clause. A guard is different. But if there's no other questions, that's it for me.
I just want to make a comment, because I think this example is such a good example, especially how you presented it, of the difference between breadth-first search and depth-first search, and especially how you explicitly change the name of the variables, which is like one I think is very interesting, because a lot of people wouldn't, and I think it's very important to talk about how naming variables matters when you're reading code. Like when you're writing code, it's actually super easy to not care about variable names, but when you're actually reading code, it becomes very relevant. But also, one line of code that subtly changed in this algorithm, now all of a sudden not doing a drastically different solution, but it's still enough of a difference to talk about. And if this was like a pathfinding algorithm, it would all of a sudden lead to drastically different performance. So I think like this is these last 10, 15 minutes is actually 10, 15 minutes that I'd point to people to actually like spend time to think about understanding BFS and DFS. I do think they're very fundamental concepts, and I think you've highlighted those differences very well. So I want to congratulate you. Thank you for that.
Yep. No, thank you. Yeah. Let me know if you guys have any other questions. But signing off.
Edwin?
Yes, Sunmin.
Hey, Sunmin.
Thank you for the explanation. I was actually going to ask the exact same question that the mentor said. Like I was wondering what was the theoretical difference between BFS and the DFS. So I see the code there is only one line that you just wrote it over there. What's the main difference between them? Sorry, I have no background knowledge, so my question might be silly.
Yeah, it's really it's the order in which it does things in terms of traversal, right? So it traverses the nodes in a different order. So in a depth first search, it's going to go through deeply into one possible path before returning back to the original node. So that's why it's called depth first search, right? So it's going to do like a deep dive in terms of like 1, 2, and 5, and then do 1, 2, 3 instead of depth first search, which patiently does 1, 2, 3, then 5. Does that make sense?
Yeah, imagine if like you're like in a tunnel system, and that breadth first search could be like going down the tunnel, or depth first could be jumping down a hole. Yeah, so you're basically like exploring in breadth first search, you're exploring each level of the tree, like each horizontal level. Whereas with depth first search, you're going completely vertical, down one particular path.
Yeah.
I have a question.
Yeah.
So actually, I just got LeetCode creating today. Is there some more efficient solution to this that we're missing? Because I noticed when you submitted it, it ranked it as a slow solution, but I'm not really seeing improvements
here. Yeah, like LeetCode is very it just may be like slow internet or something, or like just a slow judge, because I find it to be very intermittent. So like if I submit it again, it could possibly be a lot faster. But actually, it seems like it's pretty stuck here. Let me try it one more time. But yeah, like a lot of it is very precious. Now it's like 5.8. So it's like in terms of like possible ways of optimizing this. Like for example, I've been doing depth first search like this way, and I haven't submitted depth first search, just like submit depth first search. But for example, instead of using this like queue that I just constructed off the list, so the classic way in LeetCode Python would be to use the collections.the queue, and that has like its own micro optimization. So I think that would help boost the speed. And there may be ways of caching the path that you have instead of like implementing this initial string all the time. I think it's probably some form of caching that you can do possibly, because if you convert this iterative to like a recursive solution, and then I can see you can add an additional variable in terms of like a cache, and then you could pull from that cache of the initial paths that have already been built out instead of like building out the path again.
I think the string, the action part, I think concatenation of two strings is actually somewhat of an expensive operation relatively. And so what I think might help is doing that all the way after you've built out all the possible paths. Yeah, yeah, so you have like an array that you're appending to, and then all the way at the end. And then I'm sure if you're now talking returning an arrays, now there's the what if you do some sort of list comprehension on that. But I don't have any clue.
Yeah, I think the F statement is, even though it looks very elegant, maybe even doing the pluses is probably a little bit more efficient. But like, let's say like I have some kind of string path here, and then I'm like appending it to this initial string path and trying to construct two additional strings. I think that could also be a little bit more efficient. Just using one variable instead of two. But yeah, this is fairly slow, but it's right.
Yeah. I was just wondering, I immediately see some I guess strings might be taking that sort of time
Yeah, I really think that, but yeah, it's probably the F statement and the string. Yeah, because even like the recursive, like to be honest, I think this iterative solution is probably faster than the recursive.
Yeah, especially
yeah. So it is probably the F statement. Yeah, probably most of these Python solutions, most of these people don't use F statement.
Yeah.
Yeah, it's true.
This is a good example. Exactly. So I think this is a good example where like a lot of people optimize for performance in code, and I think the best solution in this is going to be maybe like 10-20% faster. Whereas the readability really goes downhill very quickly, and I think you've caught on probably the most readable solution. And I think a lot of optimization around performance is useless compared to optimization around readability.
Yeah. It is surprising though, like, yeah, until you brought it up, Andre, like, I did not, I do think it's the F statements, and I did not realize they were this slow.
Yeah, me neither. That's what I was thinking.
Yeah.
Yeah, but to cover that one that I just said, I mean, these functions that was correct. I never expect these functions in a code base, if you find them in a code base for whatever reason, implement them from scratch, I expect them to be less readable because this is really where you want performance for the ready for graphical functions. You have a higher level function, I would make the other trade off. But for these, yeah, I would definitely say
Yeah. But yeah, that's it. If there were no other questions, time for pizza.
And a Coca-Cola.
Yeah. And a Diet Coke. Yeah.
That's our sponsor.
Yeah, we're gonna start throwing out.
it was my pizza, man.
Merchandise.
What's your address in tech? I tease. This is down. All right. Anyway, thank you, Eric. Honestly, this one like got me very excited because I've been talking about it for a while with like getting Edwin's things, all of Edwin's LeetCode ones, and making a YouTube playlist out of this.